Wildfires can have a tragic impact on any area, as we've learned recently in Oregon. Whether there's houses involved and lives and people involved, or whether it's out in the forest away from anyone. Coordinates are something that firefighters and emergency workers can use to determine where a fire is, how fast it's moving, what the area that it's covering, what its perimeter is, and that can help fight that fire. So as people are on the ground, they can get GPS coordinates, and that correlates to maps, and those maps can be used to help come up with a good plan to fight that fire. In this lesson, we're going to look at coordinates in geometry, and we're going to see how we can determine area and perimeter and distances using coordinates.
When we're talking about actual areas and perimeters of something like a forest or a forest fire, the shape's not going to be very normal or regular, and we're going to have to kind of break it into some simpler shapes. So let's look at some simpler shapes here to start off. We remember when we're talking about perimeter, first of all, perimeter is the distance all the way around something. So if we have a triangle, perimeter doesn't have any kind of fancy formula. If we have these three sides, A, B, and C, we can just call this A plus B plus C. Nothing too fancy there. Okay, if we have a square, well, all the sides are the same. We can do a little shortcut. We could say, let's just say 4 times S, S for sides there, if the side length is S. Okay, and they're all the same in a square. If we've got a rectangle, well, we have two sides that are the length of the rectangle and two sides that are W. So we can find the perimeter by taking two lengths plus 2 widths, and we've got our perimeter. Now area, let's actually start with the area of a rectangle here, because remember, area is measured in square units. So whatever this length is, whatever this width, we need to find the number of squares in here. And so squares, we could count them one by one, or we've learned since we were young that we just need to count how many are in each row and how many rows there are, and we multiply length times width. So all areas boil down to a rectangle. Now if we have a square, the length and width are the same. So we can take that side times side, which is side to the second power. If we have a triangle, now this triangle here can be made into a rectangle, and actually more generally a parallelogram, but this one's kind of nice because it's isosceles looking. So let's take that, and we could take this little shape here, and we can take this triangle over here, cut off one side, and let's give it a little flip here, and there you go. All right, so then we've got, oh look, that little triangle can be flipped up there, and we've got a rectangle. And this rectangle is length times width, or what we call the height. Instead of length, we'll use h, and then we have not the whole base of the triangle, but we have just half the base. So we have half of the base times the height. Okay, all right, and that one was kind of a cheater one because it wasn't isosceles here, but in general that formula will work there. All right, well, so what we're going to care about is what happens when we have these shapes in a coordinate plane. So we have 3 points, A, B, C. Let's go ahead and graph those. And as we're doing this, this might be kind of review here. So I would encourage you, maybe go ahead and just try this on your own there, and see, fast forward to the end here, and see what you come up with, all right? But we're going to get these lines here. So we have these 3 points, A, B, C. And if we connect them, we get a nice right triangle. Now, a right triangle, when we have a right triangle, the base and the height are 2 sides of the right triangle there. In a right triangle, you really can see that this is half of a rectangle. And so now we know that the area of a rectangle, area of a triangle is 1/2 base times height. And in this case, the length of that base looks like 5, right? And the height looks like 6. So we have 1/2 times 5 times 6, which is half of 30, which is 15. And this would be 15 squares that we don't know what kind of squares they are. So we'll call them 15 square units. All right. Well, what if we have a quadrilateral here? Let's graph these 4 points. We get our 4 points and we can connect them with some lines. And we get a shape that's not a rectangle, it's not a triangle. Do you know what that shape's called? Well, that's a parallelogram. Parallelogram because opposite sides are parallel. So we have one pair of parallel sides there, one pair there. All right? So, well, how do we find the area of that? We don't have a formula for that. Well, in a way we kind of do, because in parallelograms we can take this little triangle here and we can cut that off and we can move it on over here. So imagine, again, we cut that off and we move that over. So now we have this shape right here. And what shape is that? That's a rectangle. So the area of the parallelogram is the same as the area of that blue rectangle. And that blue rectangle is the base, which is one of the sides, and then the height, which is the perpendicular distance there. So the area of the rectangle is equivalent to the area of the parallelogram, which is going to be just not length times width, but we'll call it base times height. So we got base times height. The base is one of the sides, and the height is the perpendicular distance to the opposite base, okay? So that is going to be base times height, which in this case is going to be 5. We can just count here, 5 times 3. All right, which is 15 square units. Now, let's go back and let's talk about some perimeter now. We found the area. So what about perimeter? Well, here perimeter we've got these two sides. We have 6 on this length. We have 5 on this length. But what is this guy? Well, we're going to need some Pythagorean theorem for that, right? We can use the distance formula, but a whole lot easier is the Pythagorean theorem. Okay, so I'll call this, let's call this x. Our Pythagorean theorem says the leg squared, which is 5 squared plus 6 squared, has got to be equal to the hypotenuse squared. A squared plus b squared equals c squared. And so we can get this, square it, add it, we got 61. And to finish it off, we're going to square root. And when we square root that, we get about 7.81. So now to find the perimeter, we just got to add all those up. And we get 6 plus 5 plus 7.81. That's going to be 18.81 approximately. And we had to round off there because we were square rooting. So notice that we put this approximate here. This should probably be an approximate 2, but that is our perimeter. And perimeter is in inches or centimeters, or in this case, we'll just say UN units. Okay, but we should keep an eye out for that. What about this parallelogram? Well, we know that these lengths here are 5 and 5, both of these horizontal lengths. That's easy. We can just count them. But what's this length over here? Well, in order to find that, we need to use this right triangle. We need to use the Pythagorean theorem. You could use the distance formula also, but it's a whole lot easier to use the Pythagorean theorem on this blue triangle. Okay, so that slanted side, let's call that slanted length x. Notice we're going in this triangle here, we're going over 2 and up 3, and then we need to find that length because we're going to need to know the distance all the way around. So we have 2 squared plus 3 squared equals x squared. And so this comes out to be 4 plus 9, and this comes out to be 13 equals x squared. And we can square root that, and we can get an approximate. Sometimes we'll want to leave that exactly, and we'll leave it as the square root of 13, because the square root of 13 is an exact number. The moment we go to our calculator and we get round off a decimal, it is no longer exact. But that's 3.605, all right? 3.61, we could say. So this other side's going to be the same, right? because notice they're the same length. And we can tell that because it's over 2 and up 3. This is over 2 and up 3, the same length. And that's going to be something that's true about all parallelograms there. The opposite sides are going to be the same length. So we've got 3.61. So now to find the perimeter, which is just the distance around, we're going to add up 2 of the 5s plus 2 of the 3.61s. And 3.61 double, that's going to be 7.22 plus 10. This is 10, right? So that's going to be 17.22. And that's units. We don't know if they're inches or feet or what. So now if we look at the map of fire, here's the Obenchain fire. And here's the map of everywhere that it burned there in the forest. And we can approximate the perimeter of this using some lines here. Now this is a pretty rough approximate so that this is not too complicated. A computer would spend a lot more time figuring out more details. But we can get a pretty quick estimate. Let's see. Remember, we're looking for the coordinates here. So the distance between here, these are difference between x-coordinates. Look at these x-coordinates. And if we subtract those, we get 0.039. Now, by the way, these are GPS coordinates, so these are measured in degrees of latitude and longitude, but we can convert it later there. So those horizontal ones are easy. We're going to have a little more challenge getting these ones, so we're actually going to have to figure out this vertical distance here. That's going to be subtracting these coordinates right there. And that ends up to be 0.101 there, that distance between these two guys. And then we could use some Pythagorean Theorem to get this. If we call this x, we could take 0.039 squared plus 0.101 squared equals c squared, or x squared in this case. And then we end up with 0.117 equals x squared, and we can square root that. And we get 0.108, so that's the length of this. So that's the idea, and that's how we can work around here for this perimeter here. Again, using some Pythagorean Theorem down here. We subtract these x's, subtract these y's, and we get a vertical and a horizontal. Now we can use our Pythagorean Theorem. We end up with 0.140, which would be this other side here as well. And let's see if we can work our way around here. By subtracting these two, we get 0.064, and that's going to be the same top and bottom here. We can go get this one over here the same way, this little piece. And we get 0.03 when we subtract these x coordinates here. We're going to need this for another little Pythagorean theorem. So by subtracting these two, we get 0.52. Let's try some Pythagorean theorem for this one here. Actually caught a little mistake there. This is going to be 0.052, so we square that, and we're going to get 0.003604. And a lot of calculator work going on here. And we get about 0.060. All right, what do we got? Almost there, almost got all our pieces. Now, this one here, we know 0.101 is this side, 0.101 is this side. If I subtract this, then I get these two pieces. I don't know altogether what they are, but I know if I subtract that, I'll get these two pieces together. I don't know what they are individually. And so those two together come out to be 0.049. Again, I don't know what they are together, but or individually, but 0.049 will do together. Now, last but not least, if I want to know the perimeter of this whole thing, we can add all this up. So I'm going to add all these highlighted ones up. And that gives us a perimeter of 9.4, which doesn't mean too much to us, but we notice here that in our legend we can see that 1 mile, each square here is about 1 mile. So each 0.06 is 1 mile. So divided by 0.02, because every 0.02 is 1 mile, we get about 34.7 miles. Almost 35 miles around the edge. So you get a feeling for how how challenging it is to get a border all the way around a fire like this to contain it all. So, well, just wanted you to kind of see how that could be applied there. Lots of little detail work there, but finding coordinates and finding perimeters and areas can be very useful. So thanks for joining me, and we'll look forward to seeing you next time.